At the heart of electromagnetism lies a fundamental balance of how a field moves through space, often described as a conservation of structure. This balance is captured by a specific identity that relates the way a field swirls upon itself to its internal stretching and its overall curvature. To understand the foundation of this relationship, one must look at the mathematical framework known as index notation. Rather than treating a field as a single arrow, this method breaks it down into individual components using a specialized language of symbols. Within this system, certain symbols act as substitution operators, functioning like logical switches that allow mathematicians to swap and reorganize different directions of movement. By carefully tracking these indices, a complex, double-swirling motion can be systematically simplified into two distinct, manageable parts. The identity reveals that a vector field has three primary ways of changing. The double swirl. This represents the curl of the curl, or a measurement of how the vortex-like swirling of a field is itself rotating or changing through space. In fluids, this is often seen as a sign of turbulence or highly twisted flow. The stretching effect, known as the longitudinal part, this measures how much a field is expanding outward or compressing inward at any given point. Imagine water suddenly appearing at a source and pushing outward in all directions. The diffusion part, also called total curvature, this measures how much a specific point in the field differs from the average of its immediate neighbors. This effect is usually associated with smoothing or dissipating energy, similar to how heat spreads out until a temperature is even. In a substance like water, which cannot be compressed, the stretching effect is absent, meaning any double swirling in the flow must be perfectly and purely balanced by the internal friction or diffusion of the liquid. This structural balance is the secret to why light can travel through the vacuum of space. In a vacuum, there are no charges or currents to cause the electric field to stretch or compress. Consequently, the identity uncouples the electric and magnetic fields. Normally, these two fields are locked in a feedback loop where a change in one creates a swirl in the other. By applying the double swirl identity, we find that the spatial curvature of the electric field is directly driven by its own acceleration through time. Because there is no stretching to hold it back, this balance forces the field to propagate outward as a self-sustaining wave at the speed of light, rather than simply sitting still or fading away. This abstract balance can be seen through interactive models that use two primary variables to shape a field. One variable, the source strength, dictates the stretching or compressing of the field, while the other, the vortex strength, controls both the swirling and the total curvature. Interestingly, some fields can have a total curvature that is perfectly uniform across an entire area. In a visual simulation, this appears as a solid, unchanging color, even though the underlying field may look complex. Furthermore, while the paths of the field might appear to be straight lines, the way their strength changes, growing stronger or weaker as you move, can create a visual signature that looks like a curve, illustrating that the shape of a field is as much about its intensity as its direction.